Minkowski's four-dimensional space-time world. The negative results of the Michelson-Morley experiment point out that velocity does not behave exactly like the mathematical object called vector. The resultant of two parallel vectors of magnitude c and v is, by the vector operation of addition, equal to a vector of magnitude v plus c. The resultant vector, which results from the addition of the velocity of light to the velocity of moving reference frame, still gives the same velocity of light, and so it does not behave like a mathematical vector. Minkowski impaired great elegance to the theory by introducing a fictitious construct, four-dimensional space called Minkowski world. The basic elements of the physical world are events which are described by the time when occurred and by the space where occurred. Thus, an event has four coordinates for its location, that is t, x, y, and z. The main crux of Minkowski's theory is that these four numbers must be treated as an ordered set of four components of a vector, and a suitable algebra of such four-dimensional vectors must be built to describe the relationships between them. Consider two reference systems S and S prime, and x-axis parallel to the x prime axis, and the origins O and O prime coinciding at t equals to 0. The system S prime moves with velocity v with respect to S. Supposing that at time t equals to 0, a spherical electromagnetic wave is sent into free space from the common origin. At any subsequent time, the equations of wavefront given in the two systems S and S prime are c square t square is equals to x square plus y square plus z square, and c square t prime square equals to x prime square plus y prime square plus z prime square. These are the equations of a sphere moving out with speed c in all directions. Ct, x, y, z are the time and coordinates measured by the observer in S, whereas Ct prime, x prime, y prime, z prime, the time and coordinates measured by the observer in S prime. These two conflicting descriptions of the same physical phenomena can be reconciled if we adopt the following linear transformations. T prime is equals to gamma times t minus vx over c square, x prime equals to gamma times x minus vt, y prime is equals to y, z prime equals to z, where gamma equals to 1 minus v square by c square to the power minus half. The mathematical implications of these transformations suggest that time cannot be considered a scalar under it, and the three space coordinates do not behave like the components of a classical three-dimensional vector. But when v is far smaller than c, Lorentz contraction factor gamma tending to 1 and the usual classical meanings are ascribed to t, x, y, and z.